Hello, everyone. Today we're going to be talking about password cracking, one of the many ways to compromise credentials. So we're not talking about things like password guessing, password spraying, credential stuffing, any other, pass the hash. None of those other methods of gaining authentication to a system or compromising credentials in those ways. So what we're talking about is if you dump the hash from a domain controller or a local Windows machine, or you grab the hash from a Etsy shadow file on Linux, and then you crack the hash offline. So this is an offline attack. You can crack it with traditional hash crackers like Hashcat or John. We'll be focusing mostly on Hashcat because it's more efficient, because it's a computationally intensive task. And then we talk about rainbow tables as well for unsalted hashing. We'll talk about what that is and what that means in a moment, but let's go ahead and get started. There's five attributes of hashing, sometimes four, depending on what resource you're looking at. But I like these five here. So starting with the first one, deterministic, which means the same input will give the same output. So if you put the same input in to your hashing, and now we're talking about salts here. It's kind of out of the scope of this conversation. But if you're just using a saltless hash, the same input will give you the same output. And collision resistant, which means it is unlikely that different inputs will map to the same output. Uh, if different inputs give the same output, that is considered a collision, and we don't like that. Fixed size output. So the output will always be the same size no matter the input. So if you put hello, it's going to be the same as if you put multiple paragraphs. The output of the hash will be the same length, and we'll see an example on the next slide of that. They're one way, so they're easily computed, but you cannot reverse a hash. So if from a hash, there's no way to get um, the plain text, outside of other methods that we're not discussing here. But just with the hash alone, you can't get the input. Um, Discontinuous. Similar inputs do not generate similar outputs. So if you change one little aspect of the input, the output should be completely different and relatively random. So moving on. So as you may know, hashing can be used for a couple different things, notably for data integrity, since no hashes are the same. It can be used to verify that. Um, what we'll be talking about mostly is how it's used in the context of storing passwords and transmitting passwords. So rather than storing and transmitting plain text passwords, like maybe back on legacy systems, um, hashing is used to store the passwords and compare the hashes rather than the passwords themselves. Uh, and there's a couple examples there: MD5, MD4, SHA, HMAC. Those are some kind of getting older now. Those algorithms, not used as much for password hashing. Actually, those are mostly used for integrity, but many systems still use those to store passwords. But on the left, you can see the input there. So no matter the length of that input, and you can hash files as well, the output strings will be fixed, as we just discussed in the previous slide. And you have the two different hashes there. We have MD5 and SHA-1 down here. And then you can go out to this tool here and create your own hashes, or use CyberChef, or a command line tool if you want to generate some hashes. But that kind of covers that. So here we have the process we discussed on previous slides. This is the process an application would take to authenticate a user. So here we have a login prompt presented to the user to an application. The user submits their username, Bob, and their password, password here. So that password is then hashed. So then it could be any hashing algorithm, MD5, SHA-1. I don't remember which one this one was. I think it was MD5. Regardless, that hash is then compared to the password store in the database here for the user Bob that they inputted. And in this case, it does match, so this user is authenticated. But you'll notice admin here shares the same hash. So that would indicate that admin has the same password as Bob. So on the next slide, we'll talk about how we can prevent this sort of inference from identical hashes. So here we have kind of a better process than what we had on the last slide. We have a login prompt, just like before. So the difference here is prior to hashing. So before we hash, we're going to add a salt, and that salt is retrieved from the database. So there's a call made to the database to give us that salt that's added to the password, and then this new salted password is hashed, and then we compare that hash to the database. So in this case, see, admin who previously had the same password, maybe they still do, but we're unable to tell because a different salt is listed for that user. So you can see how this prevents that. If we go back to the previous slide where those match, because we didn't have those salts. So this is kind of summary from the last slide here. Identical passwords do not map to the same hash if they're salted. That's why we use hashes, or not, that's why we use salts. So here's that drawn out. Same passwords on the salted format. They are different because of those salts. Prior to hashing, they're added. But how this is relevant to password cracking, salting passwords make pre-computational attacks less feasible, and we'll talk about what that means in a moment. But keep that in mind that that's the primary reason we're salting passwords. So if salts are sufficiently long, you would have to calculate the password with every possible salt combination. So we'll talk about that now. And it should be mentioned in some cases, these are outlier cases. Some applications use a user ID as the salt, since user IDs are unique, not usernames, because usernames can be the same between users, but user IDs should be unique, at least between users. But those can be reassigned, or depends on the application how they're handled. But in best case, you use a dedicated salt field in your database. On to pre-computational attacks, most commonly referred to as rainbow table attacks. This is the first option you're going to want to take. So if you're given a unsalted hash, the best and fastest way to crack that hash is to use a rainbow table attack. What it does, it uses hash chains. You don't need to know about the technology, or it's not. It's sometimes referred to as a database of hashes, and the passwords for those hashes, and it's a very large file. So it's instead of using resources in terms of CPU or GPU or computational resources, memory, you're using storage memory. So you have a giant table of hashes and password maps, and that's what you're just doing lookups rather than calculating the hashes. And as mentioned, it only really works for unsalted hashes. These are the primary tools. CrackStation is an online lookup, so they're storing they're essentially just storing the table online. It's accessible through this website here. You can put in your hash and it'll look it up and see if it's in there. Offcrack, used for primarily cracking NTLM hashes. NTLM is a authentication protocol. It's not a hash into itself. I'll explain that in a couple slides, I think. And then Rainbow Crack can be used to crack various unsalted hashes as well. So those are kind of your options. There's more options too. If you want to look into that, I encourage that. Look for alternative tools. There's always new tools out there. So this could be outdated in a day. Who knows? But up here, that's where I mentioned the space-time trade-off, memory trade-off. These two terms are used interchangeably. I think space-time trade-offs are more commonly used. If you ever hear that, that's what they're talking about. But moving on. So for now, we're moving away from rainbow tables, and we're going back to option 2, or I guess we're approaching option 2 for the first time, maybe for you. Password cracking by using a tool like Hashcat, or any computational. John would be one. So using hashing cycles, essentially. So how this works is you have a list of candidates, So that's usually referred to as a word list. So that's going to be your attempts. So you're going to hash all of these entries. So for each line, you're going to hash that word, and then you're going to compare that to your target hashes. So that's why it's a computationally intense process, and that's why it's faster with something like a dedicated GPU, so you can utilize those CUDA cores. But and then you'll see this example. This is Hashcat if you haven't seen it before. This is just a straight attack using rocku.txt. There's many word lists out there. You can make your own. But Rocku is from an old breach. Modified. There's modified versions too. There's a Rocku 24 if you want to check that out. And there's a few options on here, but those aren't important right now. We'll talk about those in a bit. But the two end cases, so if you just do this attack here, either the word list is exhausted, so you have no more candidates to try based on your scope that you put, or all hashes are discovered. So in this case, all hashes were discovered. You see them here, and you see some info here. During this, if it's running still, you can do like, you can tap S. I think if you press S, it'll give you the status. It'll give you like recovered, so you can see your progress here. It'll see your percentage. Keep an eye on that. I usually use that as to kind of know what's going on, but lots of information. So the key to password cracking is efficient use of time and resources. So it's really all about narrowing your scope. You don't want to do a pure brute force, and we'll talk about that on the next slide. But you want to think about the limitations or requirements of the password. So if there's a password requirement of 8 characters, you're not going to try 7 characters because it's not possible within that scope. Or you want to keep in mind the character set. So if there's a limited character set, so if the password doesn't allow for a particular character, you won't include that in your scope, either in your mask or your word list. Things like that. Look for hints. Look for patterns and other correct passwords. So if you identify a pattern or a topic or a subject, you want to maybe craft a word list around that. If you see a lot of years, maybe try some years, things like that. So you don't want to just give it some hashes and say try everything, because that'll you may literally be sitting there forever. So it's all about narrowing your key space and try to within the limitations you're given or requirements you have, what would maybe you put as a password, or what's even possible. So that's what you want to be thinking about. So real quick on pure brute forces. So what we're talking about is just basically giving it the hashes and say crack these. You're not giving it any type of guidance on what potential candidates would be. And that is a kind of a last resort. And it's not really practical for many algorithms. Most CTFs will not expect you to do this. But as we'll talk about later on, there's some hashing algorithms that are more computationally difficult to calculate because they do multiple rounds of hashing. And there's this chart here. I thought this was an interesting chart. On the top, we have MD5 hashes. So for an 8-character password, so let's just focus on this column all the way to the right. So this is my GPU. I have an RTX 2080. It would take me about 4 hours to crack an 8-character password. So that's not very strong. But if you're using a hashing algorithm like, I think this is bcrypt. Does it say anywhere? I believe this is bcrypt, but you'll see here for an 8-character password for me, it would take almost 1,000 years. So, oh yeah, it says right here I'm blind. But you can go here and read about this report if you like. It's kind of interesting stuff in there. So it's not always feasible to brute force. It depends on the algorithm, so you'd have to look into that before. And I bolded this. This is where things are heading. Slow hashing functions should be used to store passwords, and by slow they usually mean Either the algorithm's more computationally intense or they're doing multiple hashing rounds. And you can do that with something like MD5. You just hash it a ton of times before you compare the last hash. So let's say if you set 1,000 or 5,000, and then you compare the last hash. We'll talk about that, but I just thought I'd mention this report that I came across. Slow is strong. So this kind of phrase, both relating to passwords, you may have heard length is strength. That's on the requirement side. Slow is strong. That'd be on the hashing algorithm side. So systems leverage hashing rounds to increase the time it takes to crack passwords. So they're doing this to prevent, so if there's a breach or the hashes are dumped, it's to make it a lot harder for for adversaries to crack those passwords if they obtain those hashes. So, and if you think about it like this, an extra second, because when you're doing all these hashing rounds, it does make authentication take longer, but a second longer is insignificant to the user, but catastrophic to password crackers. So if you multiply that 1 second by thousands and thousands of password candidates and hashing, that's going to add up, as you've seen in that table. But Hashcat does have this is a brand new, I think it's maybe a couple years old now. But in the grand schemes of things, it's relatively new. It's -9 association attack. This is used for targeting salted work intensive algorithms, and those are done. Some of them are down here. There's more every day, but at the time of recording, these are kind of the big players. YesCrypt, that's used on a lot of Linux. I think that's used on Kali, Argon 2 script, Scrypt, PBK, and Bcrypt. So those are some hashing algorithms that are fairly slow. Moving on. So what is a hashing round? Well, it's exactly what it sounds like. So when the user submits their password, that password is hashed with the salt, and then rehashed a set amount of times. So it could be 1,000. So your password's hashed, that hash is hashed, that hash is hashed, and so on for how many rounds the algorithm has set. And then finally, once that's complete, the hash is compared to the store, and the user is authenticated. Ignore the extra store here. I must have messed up at some point, but that's how that works. There, I fixed it. On to hash identification. Over time, you may become familiar with some of the formats. I mean, you can count the characters by hand and then look at what the character set includes. That's all these tools do, but I mean, these are saving you a lot of time. But they're not 100% accurate because hashing algorithms, many of them share the same character set and they share the same the same key space essentially, if you look at it in those terms. But sometimes you can look at if they have salt or not. Anyways, Hashcat has a tool, Hashcat identify, and then you give it your hash, and you can look at all the. Let me pull this up. See if it loads. Here we go. So here we have all the supported hashing algorithms for Hashcat. You'll see there's quite a few of them. So go on and on. Go ahead and memorize this. Not really. So there they are. I mean, you can Control F this, and you can either look for, if you want to look at that. That's NTLM, MD5. You have all different types of MD5 hashing with and without salts and all that. So it's a lot there to look at. Okay. You have some command line tools. Kali comes pre-installed with a couple of them. Hash ID and hash identifier. Those are two of them. This one here is hash ID. You can give it your hash and it'll give you a list of options, what it might be. CyberChef, analyze hash. I think that one works actually. That's like one of the best that I've seen, at least for some of the common hashes. It doesn't give you a list of too many obscure ones. And then online hash analyzer tunnel up, check that out. So try a couple, see if they match, maybe compare results. Have fun with that. Now let's talk about Landman hashes. This is legacy Windows, but it's not that legacy. Depends on what kind of environment you're looking at. Landman's not good. It should be disabled on any and all systems. The reason it's not good is because its key space is so limited. So what it does is it converts your password to all uppercase prior to hashing, so that cuts all of the lowercase out of your key space. It pads the length to 14 characters with null characters, so you have a fixed length password, essentially. You might be saying, wow, 14, that's not that bad. Well, that 14 character password is split into 7 character halves and hashed separately. So it's 2 passwords combined. So it's 2 7 character passwords fused is what it is. So each half can be cracked independently. I have an example down here of that happening. So you can do this, and you can split. So mid recording on that slide, I did notice a mistake. It'll help you understand this concept more though. I had the password cool pass down here, cool password, and I showed how that's converted to all uppercase, and then it's hashed. But the mistake I made when I split those, so these are actually two hashes combined, and that's how a full Landman hash is created. So that's the front and the back half of the password. But if you look, this is 1, 2, 3, 4, 5, 6, 7, 8. So that's actually 1 too many, and that would go to the second half because it's split up by halves there. So that's how it would actually be split up by 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And these are just spaces here. So null characters. I just put underscores there to represent that. So that's how we have that. So as I was saying, you wouldn't, since this is an unsalted hash, you probably wouldn't want to brute force these. You would just use a rainbow table attack. But due to the limited key space, they can be brute force as well. I've had limited success with that in Hashcat, since you have to separate out the hash halves for LM and then brute force them separately and then recombine them. It just doesn't make a lot of sense to do. But and here in Hashcat, we can kind of play around with the weird properties of Landman hashes. Let me zoom in a little. So if we put password, say characters, take a look at this first part here. So the first half of the hash, essentially. So see, if we put another character, only the back half changes because we're now in that second portion. Or if we go backwards, now we're altering the front portion. See, the back portion's not changing. In this pattern, this AAD, that this is an empty Landman hash. So if you ever see that, that means it's only 7 characters. So kind of a weird hash. And if we do capital P or lowercase p, see, the hash is the same. Doesn't change based on case because it's all converted to uppercase. And as mentioned, you can there we go. You can try to crack these in Hashcat. You'd have to break them up like this, brute force them, but probably not worth doing. But if you find a way to do it efficiently, let me know. I'd be interested in seeing about that. There's not a lot of documentation on it because people just use rainbow tables since they're unsalted. But if you have a script that maybe does it more efficiently, I'd be interested to see that. So NTLM is a more modern Windows authentication protocol, and it uses NT hashes, and it pairs them with the LM hash if LM is enabled. So an NT hash, unlike LM, allows for lowercase characters, so we have a larger character set to use, so it also has a larger key space. NT is combined with LM as mentioned, and they're often separated by a colon. So when you do a hash dump from Windows, it'll display with a colon like that. And if LM is disabled, it'll just have this AAD we just talked about. See, it's repeated. So that's two null halves of an LM hash. So this is the same. So that'll be there in its place. So an NT hash and an LM hash, they match because of the same password. So you'll have this here, and you'll see the LM hash is before the NT hash, which is a little confusing because of the name. So it's LM and then NT. And if LM is disabled, it'll have the empty hash for the LM and then the NT hash. So cracking NT LM hashes is extremely easy. You can use a rainbow table tool like offcrack, since it is unsalted. It really targets the LM hash since the key space is more limited. You can download you have to download the table separately from offcrack, and it's kind of tedious. Let me get my pointer here. You'll see I have I made a folder XP special and put the tables in there from that website, and then you have to load the table, and then you have to enable. So you have to install and enable the table. So make sure it's all green from your folder, and then you have to load the hashes. So you just select your text file of the hashes listed. See them here. We have the NT and LM hashes lined up. Go to the next slide. So when we click start, it's really not that long till we finish. So this took about 2.5 seconds or 2.5 minutes to find those 10 hashes. And you'll see here, to illustrate the points I've made, AAD right there. That's this empty space right here. So that's LM password 2. So they actually label them as two separate passwords for those two halves of the LM, unified password. So password 1 is the front half of that LM hash, and then it just combines them into the NT password hash. So you'll see that. So you can look at each one of these and correspond them, and that the empty hash ends in EE too. So you see all these are all empty for the back halves. So we talked about Windows and some of their hashing methods. Now let's move on to Linux. So Linux passwords and hashes used to be stored in Etsy password. It no longer is. Now Etsy password just holds user information like the user ID, group ID, some info, the home directory, and the login shell. So really not that much sensitive information. Just general user information, but it still has the legacy name there. But where the passwords are actually stored, they are stored in Etsy Shadow. By default, if you don't specify a hashing algorithm, you can store plain text passwords in here as well. Not advised, obviously, but that's why I put usually in hashed form, because they don't have to be. There's other information in here as well, not all relevant to the conversation about password cracking, but you see fields are separated by colon. So these are the standard fields here. If you want to look up more details about them, they're not all populated typically, but all time is Unix time. So you'll see these numbers here. Those are days since January 1st, 1970. The explanation here, we'll actually talk about that next slide, never mind. But so after the user here, you have the password. This long string is the password up till here. So the first $sign is the ID for the algorithm. The second $sign is the salt, and the next one is the password hash. So that is how that's broken up. So here is the standard format, as I just mentioned: the ID, the salt, the hash, password. the exclamation point indicates the password is locked. So that's what this means here, and that's what this means up here. This one is not locked. The dollar signs indicate the hash is a non-DES algorithm. So that's kind of a signifier. DES algorithms were used in the past on Unix systems. Here's the most common ones. What we have here is YesCrypt. This one here, you'll see one a lot, along with some of these ones here, the SHAs and the twos or Blowfish. But that is what we have there. So now that we have all that pretext, we can finally talk about Hashcat and cracking passwords, the old-fashioned way per se. So Hashcat, the best way to learn about it would be start with the -h if you can't find what you're looking for. The Hashcat wiki is extremely well written. There's lots of detailed information, way more than you'll ever need. But just a couple, they mention it on here as well at the end of the help page, and then they give helpful examples if you forget your syntax. So Hashcat is now without its I wouldn't say problems, but it's a open source tool. I think it's licensed through MIT, but it's not the most intuitive all the time. A couple things to help it run better. -o optimizes. I usually do W3. If you look over here, that's your workload profile. So that's high. They say desktop impact is unresponsive with a 2080 GPU. I haven't found it to be unresponsive, but I've kind of too scared to try nightmare mode. So I don't know if I'd advise you trying that as well. But if you want to, try it out. Let me know how it goes. If it's a good performance trade-off or not. But I like to work on other things while I'm cracking passwords, so I don't want to go too crazy. If things don't run well, maybe do 2 or 1. This will show your devices. I should have marked that better, but I think that's an I. It'll show your devices. Use a GPU if available, so you can specify your device in your device type. That's down here at the very bottom, the Ds. So you can you look at what you have and do like D1 or D2 depending on what numbers your device is. Oh yeah, here it's -I. So that'll give all your information about your system, what drivers you have, and things of that nature. So I think OpenCL 3 is the correct version for that. If you have driver issues, look at these help pages. Be careful with that sort of thing. I don't want you to brick anything, but I'd say if you have significant issues, just do it in Kali. You're gonna take a performance hit, but at least your computer still works. So. But if you're comfortable working through things, definitely look into all Hashcat's helpful guides. I think I mentioned all these, and I think it's dash benchmark. Well, let me pull that up actually, because that's worth mentioning as well. So let's run a benchmark, see what we get. I just installed this new version of Hashcat, so it might not even work. Oh, yep. What's it say? Oh, it's opened up in the wrong spot. Whoops. Here's the correct terminal. So far so good. Device 1 is my GPU. Device 2 is my CPU. Those are my options that I specified. I don't know how long this will take actually. I haven't done it in a while. I'll cut here and come back. So I quit that and just did -M0, so that's MD5, because it was just running through a whole bunch of them. So there's that. That's how you benchmark. So here's some basic options. Dash M sets the hash type. Um, there's that same list of hashes we went over on the one of the first slides. Um, here's the from the help page. So dash M and the number. You can also use sessions if you like. If you're going to be trying lots of different things, you can save your progress. I've never really used them much in CTFs, but if you're in the future doing like an assessment or something, it's worth knowing about. So how you see your results. There's a ton of different ways for this. You can go manually open the pot file. You will find that in your hashcat folders. That's where all your hashes go, and they just stay there unless you empty them. You can specify an output for them with -O if you like. If you like to do it per challenge, or if you like, if you wanted to have a deliverable of them, you can use the -show command down here. So that shows you all your correct hashes from a hash. So you just give it the same hashes text file that you cracked, and then you do the show, and then it'll take the pot file and look for those hashes and then print those out essentially. So and -- left will show you what you have not cracked from that. So here's an empty one. It's not cracked. So it's a space or an empty. And -- user will add back user info. So if you did, I don't have an example here, but it'll put the username. If you had that in your text file, it'll put that next to it. So now we finally get into all the different attacks you can do with Hashcat. So there's really 5 main ones. There's really 5, but there's a new 6th attack that I've never really used, but worth knowing about. It's not available on all versions of Hashcat. I don't think it's on my Windows version, but it is on the Kali version. Anyways, starting with number 0, the straight attack. So all that does is it attempts every word, every entry in a word list. So that's it. So you specify your attack type with -A. You add the ID. Here they all are listed at the top, all the IDs. So that's your mode. That's your hash type. Those are your hashes. That's your word list. Here's the optimize option. Here's the work profile option. And combination attack. That's number 1. That's attack mode 1. It uses two word lists and appends each word in word list A to each word in word list B. Now, I used to use this attack sometimes, but I don't really anymore. I use masks and rules mostly now. I like to do a lot of the word list amalgamations and alterations prior to running the attack. I don't like to run it with my attack because, I don't know, that's just how I kind of do things and keep track of things. But if you want, it's totally fine. You can do that. You can maybe have we'll talk about some situations where you might want to combine words like that, but numbers or characters on top of dictionary words or something like that you can do. So here you have tech type 1, hash type 0, your first word list, your hash list. So you have your hashes just like before. You have your first word list, and then you have your second word list. So that's how you do that one. So this attack type is I don't know, it's kind of weirdly named. It's attack type 3. It's called the brute force attack mode. It should be more known as the mask attack mode. So this is just mask attack. So you specify a pattern to match, and then Hashcat's going to attempt every possibility of that pattern. So here we have we're running Hashcat with attack mode 3, same hash type. Then we can specify a pattern. So here we have NCL LMNO dash D D D D. So what these D's are, with these question marks, we're specifying a character set, and we'll talk about character sets on the upcoming slide. But just know they're placeholders. In this case, they're digits, so 0 through 9. So this would try 10,000 words. Yeah, so that's that one. So you could put anything. You can get real creative with these. Typically, you do them when you identify a pattern, or if you're doing pretty close to brute force attack. You can do this too. So so back to LM hashes, you know that they're 7 characters long. You can limit it to that. You do a different mask of that many characters, or that it doesn't have lowercase letters. You can specify just uppercase letters, stuff like that. So you can get real creative with these. And then these next two are used pretty often. Really, these bottom ones, really, I don't know. I guess all of them, except for you're probably going to use combination least often, but appending. So it's a hybrid wordless attack with a mask. So it's a combination of a straight attack and the brute force option, really. So that's -A6. I don't really know where they got the numbers from, but if you can find out what the rhyme or reason is to these, I'd be interested. But anyways, we have our hashes, we have our word list, and then we're appending. So we're doing a D and an S, a D and an S. So what this is, the question marks are marking a character. And the D and the S are 2 different character sets that we're going to try. So that's digit and symbol. And I guess I can ignore everything else in this slide except for this top portion. So our character set, D, numbers, symbols, all these symbols, and then the spaces right there. So we're going to try to know how many entries this would be. You would have to you could take your number of characters, in this case 2, and raise that to the power of how many your total character set. So you would add D, your digits to your symbols. That's how you figure out your workload, that what that's going to add to your word list, because it's going to try that for every entry in your word list. So you'd also have to multiply that by your number of entries in your word list. So you can see how this would increase your time quite a bit. Just add in two characters. So that's why scoping is so important. Last but not least, we have prepend. So it's the same exact thing, except instead of appending, we're prepending. So really, it's the same attack. We're just changing the location of our mask, and that's -A7. So we just put 2 digits, two numbers in front of our word list entries. So sorry. So 10 raised to the power 2, that's 100. So that's not too bad. 100 times however many entries are in here. I don't know how many is in RockU, but there's quite a bit. So multiplying that by 100, still significant, but it's not going to take as long as this one, because that was the special characters too, however many entries are in there. So and this one was 10,000, so big difference there. So let's talk about masks a little more in depth. We touched on them in the last slide. If you want to learn a lot more, go to this link or search Hashcat mask attacks. Learn all about them. But masks are used to set your key space for password candidates. Either expanding it or shortening it if you're removing possibilities. The placeholders are set with question marks, as you've seen, followed by the character set identifiers. You can do multiple identifiers per placeholder. And you can use custom mask files. Not going to cover those, but you can look into those as well. If you're using complex masks for a very specific thing, you might want to save those in a file and just reference the file if that's easier for you. But some examples. So we talked about this concept of character sets and key spaces, but say we have Ferris rules, digit, 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 digit. So that's 4 digits. It has a key space of 10,000. There's 10,000 possibilities of this, just like our other example we had in the last slide. We take that number of character positions there. So we have 4. And then our character set for one of those positions. This is our character set right here. There's 10 characters. So our key space is 10 raised to the power 4. And that's 10,000. So just like a, keypad. But yeah. And if you add a mask to like a word list, you just multiply whatever formula you got to that number of entries in that word list. So here's an option that is very, very useful. It's the increment. You do that with -i, and then you can set a min and a max. But you can just do -i if you want to do the whole gambit. But by default, masks are fixed length. So let me go back to the previous slide. Let me go back 2 slides. This example here, this brute force example, this wouldn't try two numbers. It would only try the 4 numbers. And this, so the last example here, this would only put 2 numbers in front of each entry in the word list. It would never do 1 number in front of it. So increment's a way to try multiple entries or multiple placeholders without trying all of them at once, kind of doing, adding one by one. So here's a couple examples. When appending or prepending, it's often best, and not only, I would do this in this example too at the bottom, but really anytime you're using masks, it may be useful to do this attack here, where you have the -i at the end. Or I think you can put it anywhere pretty much, or mostly, I guess, wherever you have options. So you're going to be adding one placeholder at a time. So in this first one where you have the rocku.txt, and then you're doing ds, 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 so that's 4 characters. It would first do rocku just this one. So it would just do, all right, let's try every digit and symbol there. Okay, that didn't work. Let's do rocku we'll do every entry in rocku with 2 digits and special characters, so, or symbols. And it would go one by one like that, adding these placeholders, increasing in length. And this is commonly done if you have some pretty good hardware. You can brute force a lot of unsalted hashes using increment. And you can set, let's say you want to have a max of 8, a min of 1. You can do all. And it would first try 1 digits, 2 digits, 3 digit password, 4 character password, 5 character password, and just keep increasing one by one until it's done. So that's how increment's used. And I don't think I covered it. Make sure I want to cover all these character sets. L's lowercase, U's uppercase. Digits we talked about a lot. I don't really use these hex ones. Special characters, symbols. A is all, so that's all the main ones. And then B, which I don't use either. So here's kind of a more advanced strategy. You can create your own character sets. So you can actually set variables, list a bunch of characters, and then specify that in your masks. So here we have an example. I showed first the passwords. This particular attack would target. So we have Ferris, we have capital F's, lowercase f's, we have years, we have 2-digit also. We have some special characters on the end. So you specify your character sets with dash number, and then I did lowercase f and capital F. I did pretty simple examples here just to make it easy to follow. And I set -2. I set 2 to 0, 1, and 2. So I put a placeholder of 1 here. So the question mark sets the placeholder. I did 1, so that's the F's. I have my static, candidate entry there. and then I have question mark 2, so that's our 0, 1, and 2. So I have that after the 20. So what I'm trying to do here is get you know it could be the year 2000, it could be the 2010s, it could be the 2020s. So that's what I'm trying to get at there. And then I did dash D, so that's just another digit. And then I did a symbol. And then I did increment to just try the first one. So that's how I got this here with just that first option. I wouldn't have got that if I didn't have dash I. And that's how I got these up here without trying. I don't think that, yeah, that's not right. Yeah, that wouldn't have cracked. Those must have been in my pop file before I ran this attack. Ignore those. But here I have my key space completely written out. Here, if you want to read it like this, so these are the variable options, static options. Those are all the options there. That's all the options at the end. So you could add these up, do some math to see how big my key space actually is. But that is how you do custom character sets. Sourcing word lists. This is often a pretty tough part of it's a tough part of password cracking in general. A lot of the lists, especially rainbow tables, not word list, kind of a tangent. They're pretty hard to find because they're obtained from breaches generally. So if the breach is fresh and it has good passwords in it, it's not always super obtainable, but it's neither here nor there. There's still a lot of great ones out there. Plenty to use up all your cycles. So Kali has some pre-installed ones at user share word list. Go check that out. Probably start with RockU or RockU 24 or one of the variants. There's a couple different ones. And then Cyclist. There's a ton here. I could probably pull that up. They're there. There's all kinds here. So a lot of them are pretty old. That don't mean everything though. There's some old good ones, but language specific, even Spanish, I guess. So yeah, browse away. And I should mention the file type txt can help you find specific lists. Wikis are a good place for finding tables. We'll talk about creating word lists in a moment. But always check if you need a list of Pokemon, do file type txt, or a list of characters from a show or anything. See if you can find it out there already, so you don't have to make it, because sanitizing data is tedious. So creating word list. If you notice patterns or themes, you may want to do this. Otherwise, maybe not totally worth it. You want to really tailor your word list to in the real world, you would want to tailor one to the organization. So you would want to use words related to the field of work, or related to the business. Names. You could do some social engineering, some info gathering around a certain individual, their hobbies, that sort of thing. So you can do it at the organizational level or the personal level. But for CTFs, they'll make any patterns known either through previously cracked passwords, or they'll give you a hint. Altering existing word lists is a good start. Using masks and rules, or create variations in word lists. We'll talk about some Hashcat utilities, at least one, surrounding kind of creating the word list. As I mentioned, wikis for characters, teams, cities, sports teams, movies. You just want to copy those pages and put it in Excel or a Word document or text file to clean up. You can use Excel, command line, regular expression, or maybe AI if you're good at prompt engineering. You can script this stuff if you're good at data handling in Python or something. All kinds of ways to clean up data, but you'll use a lot of methods if you've done log analysis. A lot of the same methods here to remove spaces, blank lines, all commas, artifacts, colons, um, all that good stuff. So let's say you're cracking some passwords and you notice a pattern of Marvel characters in the passwords, or there's a hint in the challenge prompt indicating that the passwords may contain characters from Marvel Comics. So the first thing you would do, the first thing would be to see if there's an existing list of characters. But if there's not, you can search for something like this. I spelled Marvel wrong, but that's okay. There you go. And then the first result is this here. I already clicked on it earlier just to confirm. So then you have a list like this. Many cases this will come from like Wikipedia. Wikipedia has a lot of tables and lists and things like that. And if you can, in this case we can just highlight it all, copy that. Now you can bring this to Excel. You could put it in a text file and do editing in command line in Linux if you like, but I use Excel mostly, so you can paste there. Yep, that's fine. So now I have a list of characters, and the first thing you do is clean this up. So you see we have brackets of character variations, kind of duplicate things like that. The first thing I would do, you do the replace. So I'm just going to put a blank character in. So I just put or not a blank character, but I put a space in there. I'm going to replace that with nothing just to get rid of all the spaces. So I'm going to replace all. And then let's say for all of these parenthesis items. So let me zoom in a little for you guys. So there might be a case where you want some of these items in parentheses. They're the names of the characters. So you might want to separate those out. But in this case, let's say we just want the character names. So the hero or villain names in there. So what we're going to do is we're going to do in parentheses, we're going to put star in. So star is a wildcard. So that means anything in parentheses, we're going to get rid of that. And we're going to replace that with nothing. So replace all. Oh, I see. So I still had the space there. So we already got rid of the spaces, so that wouldn't be there. I left that from the last thing we did. So there we go. It's correct now. And I want to replace that with nothing. So anything with parentheses, we'll just replace it. And then you see 313 replace. And then over here, all of those parentheses items are gone. And then next, now we're going to have variations of the same character. So you see there's a bunch of Black Panthers here from the different individuals that had that title. So we're going to deduplicate. So you can also do that in Excel. And there we go. We got rid of 183 duplicates. And then if you wanted to, you could go through and get rid of each individual. These were the headers from the different letters. So you get rid of those as well. So we got pretty clean data there, relatively. There's a couple of things, but next up, you can do something. So you're going to want a couple variations of these. Probably all caps and all lowercase are two common formats for passwords. So we have what's called camel case, where you have the first letter of each word. So that's okay to keep those. But we might need to add some more and combine into a bigger list. So you can do this in Excel. I think TR, let me look that up real quick. You could do this in Excel as well, like any of this. For the most part, you can do it in Excel. But yep, you can do the TR upper or lower to do this as well. So if you're working command line, that would be your way to do that there. Because this is all going to be copied and pasted into a text file at the end of our manipulations anyways. So anyways, you can do a equal upper, and then we just select our first cell there, A1, and then enter. So that's already uppercase A, but then we can just double click there and it'll auto populate. So now we have the standard, we have the full uppercase, and we can do a lower, I believe. Do a lower of, it doesn't matter what column you can do. I'll do B1. There you go. Now we have those. And you might want to get rid of some special characters too, like these periods and things like that, if you wanted to. But and this, you could look for things like this. But From there, you could get a text file. So you get a text file here. You could just copy and paste like this. I mean, you can save it as a text file too, but I mean, this is just as easy to do that. So there you go. That's kind of where you go from there. So that is how you create a word list, kind of the steps you would take if one's not already available. And then you can add a mask on top of that. So you would take that word list, put it in Hashcat, and do some masks, add some numbers or special characters after these, probably kind of the standard things. But that's where you would go from there. So Hashcat utilities, they use standard in, standard out, and they can be piped into each other or sent to a file. I provided a link, or you can search Hashcat utilities. There is a ton of utilities. I haven't even used them all, but worth exploring if you're, curious about all the tools they have to offer. It may make your life easier. I didn't know about some of them when I started, and I kind of did things pretty manually. So it'll save you a lot of work. So here's just one of the utilities, combining word list. So in Windows, they're just exes. So we have Combinator. It just takes a list, combines it with the other list, and it's as simple as that. Just one of the many data manipulation tools out there. And again, there's that link. Check them out. Here I have adjectives and nouns. That's a common format for both usernames and sometimes passwords. So I think it's a Xbox that does they do an adjective noun for their default username. So a little outside password cracking, but there's an example of me using Combinator to create that. Now I mentioned earlier how you can you can use traditional tools like Excel to create variations of words, but today I'd probably use more rules for that. I'd have just the default word list, and then use these rules to make them uppercase, lowercase, and all that. But here is the kind of the rundown of rules. They're similar to masks. I don't know. They're not really like masks. They're more altering the data itself than adding to it or being it, if that makes sense. So what you have is you have your default word, and here since it uses standard in, standard out, I provided an example here. But it permutates each word in the word list prior to hashing. It multiplies the workload a ton. So the short you want to start with a very short word list, or like a relatively short. ROCU's typically short enough for a lot of these, but even then, maybe not short enough. There's custom rules out there, or you can make your own. The syntax is not too bad. We'll talk about that in the next slide, but here's our example. This is the least speak rule. This is the entire rule on the right, so it's not that long. It's really just this, just this section here. So for one word, it provides 7 outputs. So our multiplication factor is 17. So that's not too bad. You take a word list of 10,000, and that's gonna be quite a bit more. But here's some of my favorite ones that I've used. These are kind of my go-tos. Check those out, and I think the details are listed at one of these links. Check these out regardless. These 2 links here, these are some word lists. I think there's some, or not word lists, sorry, some rules. And there's some custom ones. There's 2 that aren't in Hashcat by default. Lots of people make their own word lists and share them out. And -R is the identifier for that, the option for that. So here's most of the rule syntax. At least this is the main category of functions. Here's the link to where you can view this and more functions. So an example input would be, this. So if we use if we have the L rule, it will, we can look over here, lowercase all letters. So that's what it does. C, capitalize the first letter and lower the rest. That's what it does. This is prepend. So we have prepend and then we put 4, so it prepends a 4. This is C, so it's like a camel case. Invert capitalization, yeah. Then U, uppercase all letters. So those are rules, and if we go to a previous slide, that's what it would look like in the file, just like that. So cracking files isn't a whole lot different than cracking any other hashes. It's just a matter of getting the hash. So PDFs, for example, you can get the hash, extract the hash by using PDF to John, which is part of the John Bleeding Jumbo. It has a couple dependencies as well, PyHinko and exiftool. So you'll need those. And you can look up how to install this, but you can also use this here, wget, and then you unzip it, and then you copy it. I use the Py one. There's a Perl one too. But here I do the PDF John, and I specify the encrypted PDF, and then it gives me the hash. I look up that hash. I use the identifier there. I looked that up in our Hashcat supported hash list here. I just did this by hand rather than using an analyzer because it was easier. So there's only one format with that. So that's the one that I use here. And I use RockU. And it was in RockU. It was Coral 2912 right there. So, yep, find the hash. And that's pretty much it. And kind of a fun little last thing, Hashcat Brain. You can get a Brain Docker if you want. You don't. This is totally outside the scope of, a CTF, but it provides a way to do distributed cracking on like a team. It hashes your attempts, so clients don't perform the same work. It's essentially decentralized hashing, but kind of a cool thing if you want to look into it.